In this section, we'll be using our fundamental identities to evaluate functions, to simplify more complex identities, and even to solving equations. First, let's recall a few of our identities. We have our six reciprocal identities. We know that sine of u is equal to 1 over cosecant of u, and cosecant of u is inverse of sine u. Cosine of u is 1 over secant u, secant of u is 1 over cosine u, and we also know that tan u is equal to 1 over cotan u, and cotan of u is equal to 1 over tan u. We have our quotient identities. We know that tan u is equal to sine u over cosine u, and we also know that cotan u is equal to cosine u over sine u. We previously looked at one of our Pythagorean identities, which was sine u plus cosine sine squared u plus cosine squared u is equal to 1. Now if we divide all this by sine squared u, we divide this by sine squared u, divide this by sine squared u, and divide this by sine squared u. Sine squared u over sine squared u will go as 1. Cosine squared u over sine squared u will go as tan squared u. And 1 over sine squared u will give us secant squared u. So by dividing by sine squared u, we get our second Pythagorean identity, which is 1 plus tan squared u is equal to secant squared u. To get our third Pythagorean identity, we divide everything by cosine squared u, which gives us cotan squared u plus 1 is equal to cosecant squared u. We'll be looking at a few more identities, but you need to keep all these handy, commit them to memory, or have them on a sheet of paper as we go through the section. Here we have two additional set of identities. We have our cofunction identities and we have our even and odd identities. We have the cofunction of sine of pi over 2 minus u is given as the sine of cosine of u, and the cosine of pi over 2 minus u is equal to the sine of u. And we have our four additional cofunction identities, and below here we have our even and odd identities. We know that the sine of negative u is equal to negative sine of u, and the cosecant of negative u is equal to negative cosecant of u. We have cosine of negative u is equal to cosine of u, and the secant of negative u is equal to the secant of u. So these two are our even functions, and the other four are odd functions. So the cosine of secant of a negative angle is the same as the cosine of that positive angle. Here's an example of using our fundamental identities to evaluate all six trigonometric functions. Here we're told that sine of negative x is equal to negative 1/3, and we're told that tan of x is equal to negative square root of 2 all over 4. So tan of x is already given, so we have one of our six trigonometric function. So this will be 1. We're told that sine of negative x is equal to negative 1/3. We know from our even and odd functions that sine of negative x is also equal to negative sine of x. So negative sine of x is equal to negative 1/3. Therefore, sine of x must be equal to 1/3. So here we have our second trigonometric function. We know that cosecant from our reciprocal identity is the reciprocal of sine of x, or cosecant is equal to reciprocal of 1/3, which is just 3. And this gives us our third trigonometric identity. We know the reciprocal identity of tan is that cotan is equal to 1 over tan. So our reciprocal of tan, so this becomes negative 4 over the square root of 2. By rationalizing the denominator, this gives us negative 2 radical 2. So now we have our fourth trigonometric function. So then all we're left to find is cosine and secant. We know from our reciprocal identity that tan is equal to sine over cosine. By multiplying across like this, we get cosine is equal to sine over tan. We already know sine is 1/3. We already know that tan is negative square root of 2 over 4, which was given. Simplifying this, we get cosine of x is equal to negative 2 times the square root of 2 all over 3, which is our cosine. So this is our fifth identity. And to find our final trigonometric function, which is our secant we know from our reciprocal is 1 over cosine. So this becomes 1 over this. So it becomes negative 3 over 2 radical 2, which simplifies to give us negative 3 radical 2 all over 4 for our secant. Here we're using the fundamental identities to simplify two expressions. Our first expression is cosine beta times tan beta. We know one of our identity is that tan beta is equal to sine beta over cosine. So we can rewrite this as cosine beta times sine beta over cosine beta. Here we'll see that cosines cancel, so this simplifies to just sine of beta. In this example, we have secant squared x times 1 minus sine squared x. We know one of our Pythagorean theorem identity is that sine squared theta plus cosine squared theta is equal to 1. So from that, we have 1 minus sine squared theta is just equal to cosine squared x. So this becomes secant squared x times cosine squared x. One of our reciprocal identity is that cosine is equal to 1 over secant. So we can rewrite this as 1 over cosine squared x times cosine squared x. The cosine squared x will cancel here. So all this simplifies to 1. Here we have two additional examples of simplifying trigonometric expressions using our fundamental identities. Our first additional example is that we have 1 over tan squared x plus 1. We know tan squared x plus 1 is one of the identities or Pythagorean identities, and all of this is equal to secant squared x. So we could replace this with secant squared x. So this becomes 1 over secant squared x. We know this is one of our reciprocal identities now. We know 1 over secant is the same thing as cosine, so this simplifies to cosine squared of x. Here we have sine theta times secant theta plus cosine theta times cosecant theta. Well, we know secant is 1 over cosine. So if we replace that with 1 over cosine and we multiply sine times 1 over cosine, we get sine of theta over cosine theta. Plus, here we know cosecant is 1 over sine. So this becomes cosine theta over sine theta. Now because we're adding these two fractions, we need a lowest common denominator, which would be the product of these two, which is sine theta cosine theta. So if you multiply this one by sine theta, we multiply the top by sine theta, we get sine squared theta over sine theta cosine theta. Plus, multiply this side by cosine theta. So we have cosine squared theta over sine theta cosine theta. Now we can add these two. So this becomes sine squared theta plus cosine squared theta all over sine theta cosine theta. We know sine theta plus cosine theta is our first Pythagorean identity, and all this is equal to 1. So this becomes 1 over sine theta cosine theta. This now takes us back to our reciprocal identities. We have 1 over sine, which is cosecant theta, and 1 over cosine, which is secant theta. So here we have our answer for this in its simplest form. In these two examples, we're using our fundamental identities along with some of our algebra skills to simplify these two trigonometric expressions. In the first one, we have a binomial. We can see from this binomial that sine squared x is common to both terms. So sine squared x is our GCF. We can factor out our GCF of sine squared x, which leaves us with secant squared x minus 1. One of our Pythagorean identities is tan squared x plus 1 is equal to secant squared x. So secant squared x minus 1 will be equal to tan squared x. And this is times the sine squared x that we have. So here is our final answer. Here we have a binomial over a binomial. Our numerator, cosine squared x minus 4. Both terms are perfect squares. So this is a difference of two squares. We can factor the numerator, which gives us cosine x minus 2 times cosine x plus 2. And this is all over cosine x minus 2. We can see from this that our cosine x minus 2 will cancel with our denominator, which leaves us with cosine x plus 2 as our simplified answer.